Alright, silly people, here's the situation. This is the wave function for a particle in free fall, supposedly, because it's just a particle that is subject to the potential V equals mgx. And we're going to run this through the Schrodinger equation, see if it satisfies it, and then also check the expectation value of x and see if you get a sensible answer. I will note that this problem will depend on results and a definition, or a couple definitions from problem 221. I recommend go watch that video before you watch this one. I'll link it in the description, but also let's get into it. So this is the way that Griffiths wrote it, right? For the purposes of checking it against the Schrodinger equation, I'm going to have to expand the definition of psi naught, first of all. This is from problem 221, but psi naught of x and t was given by 2a over pi to the 1/4 divided by gamma e to the minus ax squared over gamma squared, where gamma was defined like square root of 1 plus 2 h bar at over m. Right. So let's write our wave function in terms of that stuff then, and collect all of the exponents under one bracket. So we have 1 over gamma, 2a over pi to the 1/4 exponent. We've got the stuff coming from psi 0, which is minus a over gamma squared, x plus gt squared over 2 all squared, and then the stuff coming from the time-dependent exponent here, gt squared over 6. Right. So the Schrodinger equation for this system is going to read I h bar del psi del t equals minus h bar squared over 2m del psi squared del x squared plus mgx psi. So we're going to need to do some derivatives. I'm going to do the time derivative first, or I'm just going to do the entire left-hand side. First of all, I h bar del t of psi, and so that's going to be just following through the product rule, 2a over pi to the 1/4. The funky thing about this is that gamma is time dependent, so we're going to have to take the time derivative of 1 over gamma and be left over with the exponent term, but then also plus 1 over gamma times the derivative with respect to time of the stuff inside the exponent times the exponent, right? And then multiply all of it by I h bar. So we got our work cut out for us. So taking this one step at a time, let's do the time derivative of 1 over gamma, which I'll remind you is just 1 over the square root of 1 plus 2 h bar at over m. So we got a quotient rule derivative. So it's going to be minus 1/2 1 plus 2 h bar at over m all to the minus 1/2 times 2 h bar a over m all over the quotient squared, so 1 plus 2 h bar at over m. We can simplify that a little bit, so we get minus I h bar a over m times 1 plus 2 h bar at over m to the minus 3/2. And we're going to collapse that back into the definition of gamma, so we just have minus I h bar a over m gamma to the 3rd. Awesome stuff there. then we'll switch back to our derivative. So we've got 2a over pi to the 1/4 I h bar minus I h bar a. Both of these terms are going to depend on the exponent actually, so let's actually factor out a 1 over gamma from all of it, and also the exponent term, right? But then we have in here minus I h bar a over m gamma squared plus just the time derivative of the stuff that's in the exponent, which is looking to me like minus 2a over gamma squared times x plus gt squared over 2 times gt, just a little chain rule there, minus a times the time derivative of 1 over gamma squared times the x plus gt squared over 2 all squared minus the imgt over h bar times gt over 3, again another chain rule. But that's not even it, because we also have the minus img over h bar x plus gt squared over 6, because product rule derivative. But yeah, that should be everything. And so we're going to need to take another detour and get the time derivative of 1 over gamma squared first. So that is looking like it's the time derivative of 1 over just 1 plus 2 I h bar a t over m, which is minus 2 I h bar a over m over 1 plus 2 I h bar a t over m to the second. So we have minus 2 I h bar a over m gamma to the fourth. And I forgot to write the I h bar here, but there's an I h bar. Let me write that in black. But yeah, that form is as good as we're going to get for now. So now we have the entire psi of x and t in these three terms here. So we're just going to write psi of x and t for those. But then we get I h bar times all the stuff that's in the brackets minus I h bar a over m gamma squared minus 2 a over gamma squared gt x plus gt squared over 2 minus, and then we put in this result, so it's actually plus 2 I h bar a squared over m gamma to the fourth times x plus gt squared over 2 all squared. Minus img squared t squared over 3 h bar, just putting these two fractions together. And also we still have this minus img over h bar x plus gt squared over 6. We haven't done anything with that yet. Okay, so we're going to move the IH bar in now. That's going to simplify things a little bit. So we have h bar squared a over m gamma squared minus 2 I h bar a gt over gamma squared times x plus gt squared over 2 plus 2i, and then it's actually minus 2 h bar squared a squared over m gamma to the fourth times x plus gt squared over 2 all squared plus mg squared t squared over 3 plus mg times x plus gt squared over 6. Right. Some of these terms are already fine. It's not supposed to be an equal sign there. It's supposed to be multiplied. But we're gonna keep the h bar squared over m gamma squared term, and we're gonna keep the minus 2 h bar squared a squared over m gamma fourth term, which is multiplied by x plus gt squared over 2 all squared. We're going to try to simplify the rest. So in these two terms here, we have a couple of terms which depend on mg. Just factor out mg. So mg times gt squared over 3 plus x plus gt squared over 6, right? But you still have the minus 2i h bar a gt over gamma squared times x plus gt squared over 2. Okay. We're going to keep simplifying this, right? M gamma fourth x plus gt squared over 2 all squared. The fractions that are inside of those parentheses add up to x plus gt squared over 2 because it's a third plus a sixth. So actually both this term here, which is the crazy 2i h bar agt thing, and this mg term both have the x plus gt squared over 2 term multiplying it. So we have x plus gt squared over 2 times mg minus 2i h bar a gt over gamma squared. I wish there was a simpler way to write that, but I don't think there is. Maybe a comment section could enlighten me, but right now, all I'm going to do from here is factor out the mg from the last set of parentheses. So we're going to get a mg times x plus gt squared over 2 minus 2i h bar at over m gamma squared. There's supposed to be another parentheses here, but that'll do us. That's a perfectly sensible way to write the result. And we're going to move on to the right-hand side of the Schrodinger equation, which I'll remind you is minus h bar squared over 2m del squared psi del x squared plus mgx psi. So let's start by taking the first derivative of psi with respect to x, which is going to be a little bit crazy, but it's going to be 2a over pi to the 1/4 times 1 over gamma times the exponent again. That exponent isn't going away. But then we have to take the derivative with respect to x of the argument of the exponent, like last time, which was this. Thankfully, gamma does not depend on x, so we don't have to worry about that. We just have to take a nice little derivative of this. So that is looking like x, psi of x and t, but then this derivative is minus 2a over gamma squared times x plus gt squared over 2 minus imgtx. It's not even x, it's just over h bar when you take that derivative. Right. So that wasn't too painful. The second derivative through the product rule is looking like del psi del x times the contents of the brackets, which again was this, plus psi of x and t times the derivative of the stuff that's in the brackets with respect to x. So that's just going to be minus 2a over gamma squared, right? So taking the first derivative that we already calculated, we know that this is going to be psi of x and t, and then it's going to be the stuff that's in the brackets squared. So eventually we're going to square this, and we have still just the 2a over gamma squared times psi of x and t. So let's actually expand the square of the brackets now, because we're going to have 4a squared over gamma to the fourth x plus gt squared over 2 all squared minus 4, or actually plus 4, I m a g t over h bar gamma squared times x plus gt squared over 2 minus m squared g squared t squared over h bar squared. And we still have the minus 2a over gamma squared from before. Let's move into the entire right-hand side of the Schrodinger equation now. So we're going to multiply all the stuff that's in the brackets by minus h bar squared over 2m. So we have psi of x and t minus h bar squared a squared, and there's a 2 up top with a gamma fourth on the bottom, and then the x plus gt squared over 2 all squared minus 2i a gt h bar over gamma squared times x plus gt squared over 2 plus m g squared t squared over 2, yeah, plus h bar squared a over gamma squared m. But then we also have the plus mgx times psi from before. So putting that all together, we have psi of x and t minus 2 h bar squared a squared over gamma fourth. We're going to keep that term the way that it is. We're going to keep this term that was on the end of this side, so it's h bar squared a over gamma squared m. We're going to keep that the way it is. We're going to factor out a g, or an mg from this term and this term. So that's looking like x plus g squared, or actually x plus gt squared over m. We still have this minus 2i a gt h bar over gamma squared times x plus gt squared over 2 term, which you haven't really dealt with yet. But we can, because we have that they are both multiplied by x plus gt squared over 2. That should really be a 2 there, not an m. Just the slip of the pen. And so, yeah. We're pretty much done simplifying. And it looks very, very similar to what we got for the left-hand side of the Schrodinger equation. But to write it all out, we've got plus mg times x plus gt squared over 2 times 1 minus 2 ia t h bar over m gamma squared. And that's identical to what we got for the left-hand side. I'll copy down what we got previously, but it was this up here. Quickly compare those terms. You'll find that they're the same. And then we can move on to the part of the problem where we have to get the expectation value of x, which we all know is going to be the integral over all space of x times the mod squared of the wave function over x. So it will behoove us to actually find what the mod squared of x of psi is. So mod squared of psi of x and t, considering the fact that the wave function was psi 0 of x and t times an exponent that had an imaginary component to it, the imaginary component will be canceled out, and so we just have the mod squared of psi 0 x plus g t squared over 2 t. And this is when a result from problem 221 will come in pretty handily, because we found that back then mod squared of psi 0 of x and t, the square root of 2 over pi times w e to the minus 2x squared w squared, where w is pretty much just the square root of a divided by mod gamma squared, which looks like this, 2h bar at over m all squared. Right. So all we have to do for our wave function is we have to plug x plus gt squared over 2 into x in that equation. So it looks like for us, the expectation value of x is looking like the integral of x times root 2 over pi times w times the exponent of minus 2w squared x plus gt squared over 2 dx. And we're going to make a u substitution on that. So that u substitution is going to be u equals x plus gt squared over 2. Du equals dx, so there's no need to change differentials. But we will need to get a new expression for x, which is going to be u minus gt squared over 2. Plug that into our expression for x, and we get square root 2 over pi w integral u minus gt squared over 2 exp just minus 2w squared u du. This is cool because the exponent is an even function, u is an odd function, so if you multiply those two together and integrate them, you're going to get 0. So we just have the other term, which I'm not even going to write the rest of the prefactors now, because you know it's just minus gt squared over 2 times the integral of mod squared psi dx. And then assuming the wave function is normalized, which it is, we did it back in problem 221, that integral is just going to be 1, and so we get minus gt squared over 2. Now why does that make sense? It makes sense because it's a particle that's in free fall. We assume that it's starting with no initial velocity, and so it completely obeys the kinematic equation for a particle falling down in a gravitational field, little g. I'll write it out, but it is just minus gt squared over 2 in classical physics, so it makes perfect sense. All right.